Hello everyone. So I'm Prashant Kumar. I'm a PhD scholar at IIT Kanpur. I'm working on scientific machine learning. So I will be the tutor of this course Deep Learning EE53. So in this course, we will have a weekly of 2 hours in which we will discuss the questions. We will solve your doubts and we will try to make the concepts clear. You can ask me any question on this platform, or you can ask the question later as well. I will share my email ID as well, so you can ask some question there as well. So, yeah, so we will proceed. So, in the first lecture, we have seen the introduction, then we have seen some feature mapping, and then we have seen some Bayesian learning or Bayesian method to find the error or find the difference between or to classify the two different kind of features. So the lecture start with some motivation and then we directly move into the different kind of features like a 2D feature or a 1D feature, or you can say like how different kind of feature can be used. The lecture also discusses that the generally in the traditional machine learning we use the feature extraction from our data and then we use that to figure out what are the output we want, basically classifying the outputs into different probability distributions. So in the lecture, the one of uh, the professor was discussing that let's say if you have a multiple images, either it can be a grayscale image or it is a colorful image. So in the grayscale image, the pixel values, like the, the pictures are converted into the pixels and the pixels values grow from 0 to 255. So in grayscale, you only have a one matrix of whatever the pixel size it is, the images, and the in the colorful we have the array RGB. And generally, when we deal with that, either we normalize it or we keep it in that form of 0 to 255 only. So uh, what uh, what we do generally, if you have any experience with the machine learning, uh, generally either in case of images we find the features which are very important for us, more like a, you can say, the convolution, finding the important features and then flattening it, basically like concatenating the features. Like let's say if you have one image and you have the one image of car and then you have a similar pixel size of different images. So basically you want to classify those images. So if you have a, like if you want to concatenate it, then maybe you will find the important features and then you will concatenate it and then you will give the input to the machine learning algorithm where some parameters will be getting learned and then you will get the output. That output will tell you the probability distribution of different basically different kind of classes, in a sense like once the once the algorithm has been learned, if you will give any input in that similar fashion, you will get the probabilistic output. And the output, every all the classes will have some output, but you will find that the whomever who has the highest probability distribution, you will say that this output belongs to this class or this input belongs to this class. Okay, so when we do that, we first prepare the data, then we uh, try to create some learning parameter through some algorithm. In machine learning, that these are pretty simple, but in Deep learning, you might have a multiple layer perceptrons. MLP in generally can say multi-layer perceptron or multiple, whatever you want to say. And then those perceptrons contains the learning parameter, and those parameters are trained. In general, there are multiple kind of learning algorithms depends upon what kind of uh, what we want as output. Either we want some kind of reconstruction of the image, either we want to basically uh, create some image, we want to generate some image from some previous image, or we want to basically sharpen the image, or we want to enhance the image. So depends upon the kind of uh, requirement we have, we will design the different kind of algorithms from a given set of data. And once we train that with that algorithm, the algorithm contains the different kind of network architecture and different kind of loss function and the training algorithms. So yeah, so we will see what we have learned, and then we will go through some question and answer Q&As. And if you have any doubt, we can check it. So uh, I will. So basically, the professor starts with some feature mapping, and then he goes to like the polygonal representation of any features. Like let's say if we have any cloud feature, and we want to, because any network doesn't take any proper cloud feature, it basically takes a different discrete points of that feature. So there are different way we can convert that curve into some feature, and then we can make into some kind of vector notation, and then we can give that as an input. So one of them is like a polygonal representation, in which basically you find the farthest point and then you connect them, and then the one closed curve has been converted into two different curve. I mean two closed curve, and then whatever the line you have drawn into the curve, you will find the farthest point from the light in each direction, because that line is basically dividing the curve into two different directions. In both the direction, you will basically see the farthest point, and you will create another point at those farthest point, and in the top as well as bottom. And basically, you will have a, or you can say left or right, I mean, either in the side. And in that case, you will create more points, and now you will have 4 points. Again, you will attach those 4 points side by side, and then you will try to find the farthest point. So basically, you can do this as many as possible. However, you will keep the threshold because you don't want to have an infinite number of points, because you will have a computational requirement. You will have a computational limitation in basically. So, and so you will keep the threshold for those distances from those lines. And once the threshold has been achieved, you will get certain number of discrete point on the curve, and that curve will act as a feature input for the training. Then there are the signature descriptor. Like let's say if you have any curve, let's take a simple example of a square, circle, or rectangle. Basically, first you will find the centroid, and from the centroid you will create a mapping vector called theta and the r basically. And once you will through from the centroid, when you will rotate from 0 to 180-degree, the distance from centroid to that curve will change, and that representation of theta and r in a 2D graph will tell you the feature of that shape. So you can do that as well. Or you can have a Fourier descriptor, like let's say if you have again a circle or you have a square or any rectangle, basically you will take the all this different magnet. Basically you will denote all the coordinates of that shape as a x plus y iy, and then you will find the coefficients from x and iy for the coefficients of Fourier, and then you will write the summation of Fourier. Basically, like if you want to write z equal to xk plus I yk, then you will write all the coefficients au as a zk into e to the power I to n 2 pi I k by n, where k goes from 0 to n minus 1. So basically, once you find all these coefficients, you can reconstruct those. So basically, initially you have, let's say, n number of discrete points on that curve, and then you have find all the coefficients. And if you are using first two coefficients, it means the higher frequency, I mean lower frequency coefficients, then you will be able to get a kind of lower representation of that original whatever you have tried. So basically, if you are taking a square, you have taken n number of discrete points on that surface, and then you have reconstructed the coefficients for all those x and iy. And then when you reconstructed for the first two coefficients, basically you will get a circle. Basically, it is acting like you are giving r and theta as a coefficient in some kind of notation. You can say that in that way. And if you will keep increasing those frequencies and keep adding the bigger, I mean different coefficients, you will get you will get you will go near to the original representation. And if the frequency is very high, basically those frequencies denotes the more accurate points of the original feature. And then you have the statistical moments. Basically, it tells the how the variance is of how your original feature is varying into the space, how much skewness is there. So the different kind of moments, I mean the first moment, second moment, third moment. First moment it will tell the mean of that. Second moment will give you the variance. Third moment will give the skewness of that feature. Or you can say the whatever the input you have. And then you have the regional descriptor, more like an intensity descriptor, histogram descriptor, and then some gray level correlate co-occurrence, like if you have some kind of texture in your image, basically you want to find all those texture manually, and those textures will help you to identify the output, and those texture will be act as some kind of feature in the input. And those are, and in that case there are different kind of different sorry. So in that co-occurrence matrix, there are different kind of parameters you can check. In which you can take the maximum probability, you can check the uniformity. Basically, that is also termed as energy. Then you can check the entropy. You can take the element difference moment, or you can check the inverse difference moment. So basically, element difference moment check talks about the contrast. The inverse difference moment talks about the homogeneity. So these things you can check, and you can find the different features, and you can train. And then the professor discussed about some Bayesian learning. So basically, if you have some kind of distribution, I mean, let's say if you have different classes, and if you want to, for the given x, if you want to know what's the probability of getting a class A, then you can have the Bayesian learning kind of things. Basically, you will use the conditional probability. You will use some basic base rule to understand these things, in which there are method called the base minimum error classifier. So basically, you have a distribution of two different classes, and at any x, if you see that which one is the minimum, I mean which one is the maximum, that is the probability of getting at that x. However, which one is the minimum, that considered as the minimum error classifier. However, there are even better method and to understand, and that is the base minimum risk classifier. So basically, you assign a risk, different kind of risk for a certain number of classes, and then you find the risk for all the classes. I mean, if you are giving a one risk alpha or alpha for all the x or given x, you will find how much risk you are going to take. And for different kind of actions, you will find the risk, and then you can decide that which action is giving you the minimum risk, and that kind of and that how you will decide what actions you have to take. So there are different mathematics, simple mathematics, some conditional mathematics are there. So let's see some question and answer, and then we will learn more. So if you have any doubt, let me know. I mean, no one is here, so but once this lecture will be recorded, you can watch it. I have around 20 questions, in which the 10 question I have taken from the previous rollout of this course, and I have created 10 extra questions. All of them contains the answer. So slowly I will go through all the questions. I will discuss those questions, and then you can watch it. Sorry. Yes. So these are the question. So here is a picture is missing. So basically, the picture is, I will describe the picture. Just so signature descriptor of unknown shape is given. Can you identify the unknown shape? So basically, in the picture, you have a L and then you have a theta, and the theta is constant for all the L. So basically, you have a theta is not changing for all the L, for all the R. So basically, that is showing that the that is the only one kind of shape that cannot, that from the centroid that doesn't change the distance. For all the theta, the L is not changing. Sorry. So for all the theta, the L is not changing. I mean, the R is not changing. So basically, that is circle, right? The question is like to measure smoothness, coarseness, and regularity of the region, which transformation is used. So there are different methods. So definitely you use the wavelet transform. Basically, you locally window the part, and then you find the waves. I mean, the different wavelength in that windows, and that tells you about the regularity. Okay, like in which window, what are the frequencies available or what are the wavelengths available. If in each window different frequencies are available, then you can say that it is irregular. If in some, if you are changing the window size and still you are saying that let's say in each window you have the similar kind of frequency, and even if you're changing the window size, the frequency is not changing much, then you can say that the region is very regular. Uh, then you have a Gaba transformation when you like check the different kind of co-occurrence, and so basically you are using both to check the smoothness of this picture, right? The question is, if a Fourier descriptor has k coefficient and only m that is less than k coefficients are used, what will be the effect of the reconstructed shape? So obviously, let's say the square is a very simple example. Let's say if you have a square kind of a signal and then you are reconstructing that shape, first you are writing the shape into the Fourier coefficient with the Fourier coefficients. You are able to achieve a certain number of accuracy with a n number of k number of frequencies or k number of coefficients, and then you are using m number of shape. Basically, you will get a smooth boundary, even though I mean you are not able to use all these frequencies, so you will get a very smooth boundary, right? The question is a polygonal descriptor computation using splitting technique. The starting guess is the closest boundary point, the farthest boundary point, the arbitrary boundary point, none of the above. So basically, anyway, the idea is to find the farthest point. So basically, you can do one sorting algorithm because you have all these collocation, all these discrete points. So basically, you can do sorting to find the two farthest point, and you can start from there. So that will be the most optimal way to reach the threshold into the minimum process. I mean minimum iteration. Then you have this question. Uh, just a minute. Yeah. Consider base minimum risk classified with PW1 0.3, PW2 0.7, probability of x given W1 and probability of x given W2 0.5, then and Px is equal to 0.5. If x is assigned to W1, what condition is true? I mean, you are saying that so we want that when we are classifying that thing, we are saying that the probability of getting the W1 is highest in that from for given x, the probability of getting the W1 is highest for the given x. What condition should be the true? So basically, the formula is the probability of x give the formula is probability of x given W1 by probability of x given W2 is always greater than lambda R2 minus lambda R2, sorry, lambda 1 2, yeah, lambda 1 2 minus lambda 2 2 divided by lambda 2 1 minus lambda 1 1 into PW2 by PW1. So basically, idea is like if you will find the value of PW2 by PW1 is basically 7 by 3, and these two values are given, and Px is basically so we will get the value of this so it will become PW2 by PW1 becomes 7 by 3, and then it will become 0.65 by 0.5. It will be 65 by 50 into 65 by 50 into 3 by 7. So 65 into 3 by 7 into 50. So it will become 135, and this will become it will become 65 by 50 into 77 by 3. That will become 195. It will become 150, right? So 195 by, okay, I'm getting confused. So basically it's like 65 by 50. So you can simply multiply W1 W1 and W2 W2. So W1 is 195. This is giving 195, and this is giving 350. So 350. Okay. So if you have this ratio of 2 by 1, so if this will go in this side and this side, so it will become always greater than 1.79. And then it is asking like if x is assigned to W1, which condition is true? So basically the option B is true, right? Yeah, option B is true. Yeah. The Fourier transform of a complex space Sk is written as Sk e to, oh, sorry. Yeah, so Sk e to the power minus j. No, obviously option C, right? Given the co-occurrence matrix, what is the maximum probability descriptor? 3 by 710, right? Each of the following is not a boundary descriptor. Histogram, right? So a polygon is also telling about the boundary. Fourier descriptor is also signature is also telling about the boundary. Gray co-occurrence matrix is used to extract boundary texture MMFCC zero crossing rate. Basically texture, right? If GL CM values are constructed around the diagonal, which is true, the entropy difference moment is low, element difference moment is low, inverse difference moment is low. So you have to check the formula. So the formula is like if the constructed around the diagonal, which is true. Around the diagonal means I and j equal to constant. The option element difference moment, basically the summation of ij to the power k is low, right? Yeah. Then I have prepared some other questions. So in this section, we will discuss some more questions. So let's see. So shape signature is periodic but not constant. The shape is periodic but not constant. So basically, for all the theta, the L is changing, but it has period. Like after 90 or every 180, it is changing. So basically, it's some either it can in this from the option. It's definitely not the circle because it will be constant, and it can be a square. It cannot be a line. It can be line, but it won't change from 0 to 180 and then 180 to 360. Basically, you are moving on the same line. So you will consider the answer as a B. A high frequency Fourier discounter coefficient represent the global shape centroid, find boundary details area. So option C, right? So high frequencies are the basically when you start building the coefficient, the lower frequencies starts building the smoother shape, and if you keep increasing the frequency, you start getting close to the original shape basically. So higher frequencies always captures the minute details into any uh, feature, any Fourier feature. Which discovery is rotation dependent without normalization? Yeah, so that is the shape signature, right? Just give me a minute. It's a little bit sick. So which descriptor is the rotation dependent without normalization? So basically, we don't do any kind of normalization. We just find the centroid and then we rotate it around that centroid for all the 360-degree. The Bayes minimum error risk classifier minimizes the risk variance, probably of misclassification, entropy. The option C. The yes. So risk, what the risk tells you? Like you define the different losses, and those losses tells you for all the probability for given risk. It tells you try to find the for which action the risk is minimum. So this Bayes minimum error classifier minimizes. Oh, sorry, I just confused. Yeah, this is not. They are not talking about the risk classifier. They are minimum error classifier. They are talking. They are definitely the probability of misclassification. Like what has which probability has the maximum value, and that will be taken as the probability distribution. That will be act as a classifier. With GLCM feature measure the randomness. So entropy always measure the randomness. There is no doubt. Histogram features are invariant to rotation, obviously. Translation, that is also right. Histogram feature are invariant to scaling. If you change the scaling, it might change a little bit. But okay. Scaling means either you are zooming it or zooming out. However, all the pixel values are same. In that way, so all of them will be invariants. But the idea is that I think the option should be D. Okay. The low frequency Fourier coefficient describes the noise fine details, right? Global shape, low frequency. Oh, sorry, low frequency. So low frequency is either about the global shape, right? GS image computing units, single pixel values, pair of pixels, histogram means gradients. It's a pair of pixels, right? So inverse difference moment is high when texture is random. Inverse is high. Okay. So when it will be smooth, the I minus z will become 0. In that case, the inverse difference moment will become infinite. So it will option C should be right? Okay, great. So which feature is most sensitive to the illumination change? Definitely shape will remain same, the texture will remain same. The intensity will change because the color will like a particular color, like let's say if you have a gray image and if you will change the illumination, the white part will start coming and the black will change. So they are changing the raw intensity of that. So basically C is the answer. So I mean you can see that the questions are very easy. I mean there is nothing too much. The only thing you can do is to work on the mathematics, what are the base rule, how we can implement it. You can write some code for different examples. You can work on the little bit of Fourier transform. You can also work on the some of the mathematics of the GLCM, and that should be enough of this week, I guess. Hmm. So I will basically upload this uh, content and upload this uh, changed you mean PDF, and you can watch the lecture or you can also see the PDF for your reference, and that should be enough for this week. And yeah, thank you. So I will stop the recording and I will leave you here.